very good evening to everyone. Today I would like to present on a safety project. So my name is Yogeshwaran and I would like to introduce my other of my members too. Dinesh Kumar, Chu Aungsian, Chu Jahao and Denishwaran. So I would like to move on to introduction of this my project.
Now I'm going to talk about introduction. Basically, heat exchanger is a device used to transfer heat from one fluid to another without direct contact of fluids. Heat exchangers usually maximize the transfer of heat by maximizing the contact surface area between fluids. As when the warmer fluid is passed through a series of coils or thin plates. Generally, there are three types of heat exchangers in the industrial plant. They are U-tube heat exchanger, straight tube heat exchanger with one pass tube side, and last but not least, straight tube heat exchanger, two pass tube size. Lastly, there's three main physical processes occur in this device. They are convective heat transfer from a fluid to the inner wall of the tube, conductive heat transfer to the tube wall, and the convective heat transfer from the outer tube wall to the outside fluid. So the objective of our project is to determine or come out with a most efficient and appropriate heat transfer coefficient. So there are five different members in our group, and we have given 5 different values to conduct this project. So next, my colleague will take on the next part.
Good evening. Now I'm going to talk about governing equation. Following are energy transport equations that are used in understanding and studying the simulation conducted by COMSOL software on the given heat exchanger problem. The first one is the heat equation. The formula is given in the diagram below, where all the value is defined properly. The second one is the heat flux equation. Q0 is equal to T external minus temperature and then multiplied by H, which is heat transfer coefficient. The last one would be the Fourier's law of heat conduction, where the formula or the law will be splitted or separated into 3 parts: 1D, 2D, or 3D. The formulas are given in the diagram.
My name is Jagdishwaran, ID 17207. Now we are present on methodology part.
Simulation work for this process is done using COMSOL. Therefore, each individual is required to model a complete heat exchanger in order to determine that absolute value of the heat coefficient. Groups are assigned with this identical task with some difference in terms of dimension and the heat exchanger to be modeled. Origin of this is positioned differently in the heat exchanger depending on the x and y value of each individual. There are few steps involved in this simulation. Each of the steps need to be carried out carefully and checked before proceeding to the next step to prevent errors to occur. The first step is problem identification and data gathering. Make sure that all the information is collected from the question so that we clear with the parameter or variable that we want to find out. In this case, heat transfer coefficient need to be found out so that the average outlet temperature is equal to the required temperature. Each student is given their own value to solve the simulation. Next is developing the model step. 2D space dimension is selected under Add Physics, choose non-isothermal flow, select laminar flow and then click Next. Then under Study Type, select Stationary and click Finish. The next step is building geometry. Under Model 1, right-click Geometry 1, choose and create 2 rectangles, 4 circles and 2 squares according to the values given. Under the Geometry 1, choose Boolean operation and then select Difference to subtract the unwanted regions. Then for selecting the material step, under Model 1, right-click, open Material Browser, search for the material water and then add to the model. For non-isothermal flow step, under Model Builder, Right-click non-isothermal flow, select inlet and specify the inlet region. And then for temperature, specify the inlet temperature, and the temperature is set as default at 298 Kelvin. Right-click again on non-isothermal flow and select outflow and specify the outflow region. Right-click on the non-isothermal flow again and select heat flux, specify the heating coil. The temperature is set as default at 623.15 K. Specify the heat transfer coefficient, which is determined through the trial and error. Lastly, when we proceed to the data plot step, right-click on Study 1, click Compute. To get the 2D or 3D plot, under Results, right-click 2D or 3D plot group, select Contour Surface or Isosurface, and click Plot. Under Settings, Expression, click Replace Expression button to change the temperature to velocity magnitude. To get the line graph, under Results, select Dataset and select Cut Line 2D. Specify the X and Y coordinate and click Plot. Then right-click Results, select 1D plot group and select the line graph. Repeat this with different values for X and Y coordinate to get temperature distribution. Thank you, that's all from me.
Now I'll talk more about the result parts.
First, I'll talk about Mr. Yogesaran's result. As we can see here, for his part, the heat transfer coefficient which needed to achieve at the 121 degrees Celsius is around 38.5, and this will be the optimum heat transfer coefficient graph by trial and error, and this will be the diagram for his part, where x is equal to 0.21 meter and y is equal to 0.156 meter. Next will be Dinesh Kumar's part, where for his part, the heat transfer coefficient which needed to achieve at 121 degrees Celsius is 38.5, and this will be the graph of optimum heat transfer coefficient by trial and error, and this will be the diagram of his part, where x is equal to 0.235 meter and y is 0.184 meter. Next will be Chu Hong Sian's and Jaganiswaran's part, where for both of them the value is same, so for them to achieve the heat transfer coefficient at 121 degrees Celsius is 48.1, and this will be the graph of their optimum heat transfer coefficient by trial and error, and this is the diagram which they've got, where for them the x value is equal to 0.235 meter and y is equal to 0.114 meter. Last but not least will be Chu Jiahao's part, where for his one he need a heat transfer coefficient of 48.075, and this will be the graph which he got for the optimum heat transfer coefficient by trial and error, and this is the diagram for his part, where x is equal to 0.135 meter and y is equal to 0.156 meter.
Okay, now I'm going to talk about the conclusion.
Okay, now I'm going to talk about the conclusion. The heat exchanger is used to improve the exchange of heat between the two fluids which are at different temperature. The heat transfer usually involves convection and conduction. Heat flow from region of higher temperature will be flow to the region of the lower temperature. Under equilibrium condition, temperature of two fluids will eventually reach equilibrium, where heat transfer will be equal to 0. To lower heat transfer coefficient, there are several ways to do it. First one is the position of coil must be nearer to the entrance. The length of the slit must be longer. Position of slit must be nearer to the heating coil, and the resistance time of water in equipment must be longer. And that's all for our presentation. Thank you.